Okay, thanks. This is joint work with my PhD student, Charlie Walpole. When a program is well typed, then there's a guarantee that the program will be free from a certain class of exceptions at runtime. But when a program is not well typed, when it's untypable, then there are no guarantees. It could be that the program is actually incorrect, that you can provoke it in just the right way at runtime so that you get an exception. But it could also be that the program is perfectly fine, and it's just the type system can't see it. The type system is not expressive enough to prove the correctness property. And when a program is rejected for being untypable, then the programmer has to invest effort into working out which of these two cases it is. Now, for mainstream type systems, Hindley-Milner style type systems, this is maybe not such a problem. But for the kind of sophisticated, complex type systems that we sometimes see at POPL', I think it can be a barrier to adoption. So we wanted to look at this problem, and we were inspired by the recent explosion of interest in incorrectness logics for reasoning about incorrectness in first-order imperative programs, in particular Peter O'Hearn's incorrectness logic. And so we wanted to look at what incorrectness reasoning might look like in a type system. In other words, to give maybe a type system that could give some guarantees when the program was incorrect. And what we came up with in the end is really a fundamental extension to the notion of type system. And so I think even if you don't care about incorrectness, you should find the talk interesting. Now, this new view of type systems, it comes about quite naturally if we think of type system as a kind of proof system. And if we think of a type system as a kind of proof system, then the purpose is to justify judgments. And in a judgment, of course, we say, well, assuming the variables have certain types, then the conclusion has a certain type. In other words, we conclude that some term or expression M has some type B. If we think of this as a proof system, then what we have is some kind of hypothetical statement or sequent, and the formulas out of which the sequent is built are these typing formulas, term, colon, type. And this view reveals to us something immediately, which is that there's a fundamental asymmetry baked into type systems, which is not present in more standard proof systems, say for first-order logic, which is that although we can conclude an arbitrary atomic formula, an arbitrary typing, we may only assume typings have a certain shape, namely variable colon type. We can't assume an arbitrary typing on the left. It's clear why this evolved if we think of type systems as a means to define what constitutes valid syntax. But nowadays, we're more often using type systems as a means to prove properties, state and prove properties of programs. And from this perspective, it's less clear why we maintain this restriction. So in this work, we don't maintain this restriction, we remove it. And we show that it leads really to a rich new kind of type theory, which is very natural, and it moreover provides the foundation for the kind of incorrectness reasoning that I'm talking about. So in our two-sided judgments, we can make assumptions on arbitrary typings, compound terms on the left, and the semantics is really just a slight generalization of the usual semantics for call-by-value typing judgments. So in other words, if we assume that N1 evaluates to a value of type A1 and ... nk evaluates to a value of type AK, then it follows that either M evaluates to a B or M diverges. Okay, so let's take a look at some examples. So these examples are very simple PCF kind of examples, a single base type NAT. So if we assume that the identity applied to some variable y has the type NAT, well, then it follows that y has the type NAT. If we assume that this PCF conditional, and if zero conditional, if this has the type NAT, if it evaluates to a natural number, then it follows that Z, the guard, must have been a NAT. But of course, we don't lose anything. We still have compound terms on the right-hand side. So from this formula, we can deduce that y is a NAT, and from this formula, we can deduce that Z is a NAT, and therefore it follows that y plus Z is a NAT. Now, if we allow ourselves more sophisticated kinds of types, like we see in these systems that we see at POPL', so I'm a particular fan of this system by Aiken, Vimmers, and Lakshman, which comes from POPL'24. And there they have a type theory where you can lift data constructors to the type level. So they have, for example, a type cons AB for two types A and B. And this is the type of terms that are conses, where the head has type A and the tail has type B. So for example, the list 1, 2, 3, this has this type because it is a cons whose head is a nat, whose tail is a cons, whose head is a nat, whose tail is a cons, whose head is a nat, whose tail is nil. So with these types, we can state, for example, in our two-sided judgments, that this inexhaustive match expression, here you see it extracts the head of a non-empty list but crashes otherwise. So if this has type A, in other words, if it evaluates to a value of type A, then it follows that, in fact, the scrutiny must have been a cons, and moreover, the head of the scrutiny must have type A. We also remove the restriction that ordinary type systems have of having exactly one formula on the right. So if you have multiple formulas, then it's understood disjunctively. So for example, if this inexhaustive match evaluates to an A, then it follows that either the scrutiny is a cons or Y is a nat, whatever. Now the most interesting case potentially is when you have an empty right-hand side, zero formulas on the right, because here you understand it as the unit of disjunction or absurdity. So this is a way to express that some assumptions are inconsistent. So it's not possible that simultaneously we can have that x as a function from nat to nat, and that if you take the head of the list containing x, then this is a nat. Okay, so I hope you get some flavor of what kind of expressive power having these two sides to the system gives you. But you probably wonder whether the type systems themselves, the rules, are really as natural as normal type system rules. So let's take a look. So here our key idea is really to understand type systems in a different way, to understand type systems as sequin calculi, where the only formulas are these typing formulas. And so like most sequin calculi, I mean, there are rules for justifying formulas, and they can be categorized as either being left rules or right rules, depending on where the formula occurs compared to the turnstile. Now, if you take a normal type system, then we just see it as a sequin calculus where you just have right rules. So all the normal rules of your type system become right rules, but with one slight difference, because we allow now multiple formulas on the right-hand side of the turnstile, so we have to have a context to describe this. So this is the delta here that appears. But otherwise, it's just normal, right? So, for example, to the successor on the right, if we want to prove that the successor of m is a nat, then one way to do that is to prove that m is a nat. The usual application rule, if we want to prove that some application mn is a b, then we can prove that m is a function from a to b, and prove that n is an a. So, just as normal. But more interestingly, we have left rules. Now, in sequin calculus, we think of left rules as explaining how to refute a formula that occurs on the left, but in practice, more often you use them just to extract information from assumptions. But let's stick with refutation because it's a good way to explain the rules. So for example, if I want to refute that the successor of m is a nat, then one way to do that is to refute that m is a nat. If I want to refute that this conditional evaluates to an a, then one way I can do that is to refute two things: refute that the then branch evaluates to an a, and refute that the else branch evaluates to an a. Because if neither the then branch or the else branch evaluates to an a, then the conditional can't evaluate to an a. Now, of course, things get more interesting when we try to type lambda calculi, and there we need the ability to give a left rule that allows us to refute an arbitrary application, a function applied to an argument. And for this, we need another new ingredient, but it's also very natural, and it is the necessity function type. So it's a new kind of arrow that we pronounce a only to b, and it's the type of functions that if they produce a b, then you must have given them an a. So if we compare it to the traditional arrow, if we look at the introduction rule of the traditional arrow, then we can see it kind of internalizes a certain kind of dependency between a term and its variable. Namely, if the input x has the type a, then the output m will have the type b. So if we think of a function as its purpose is to provide an output, then if we want to obtain a b from this function, then it suffices to give it an a. It's about sufficiency. So for example, The constantly 42 function, of course, if you want to obtain a nat from it, then it suffices to give it a nat. The map f expression, if you want to obtain an empty list from it, it suffices to give it the empty list. But it doesn't suffice to give it any old list. Now, two-sided judgments allow us to express a new kind of dependency between a term and its variable, which is this one. So here you can see the premise is the mirror. So here the dependency is if the output evaluates to a b, then the input must have been an a, the x is an a. So for example, if we want to obtain a value of type a from the head function, then it's necessary that we give it a cons, and moreover it's necessary that the head position of the cons is of type a. If we want to obtain an empty list from map f, it's necessary that we give it the empty list. And here you can see that with the usual arrow, we can express preservation of properties. Map f preserves the emptiness of its argument, but with necessity, we can express reflection of properties. Map f reflects the emptiness of its output. And then, of course, it's not the case that to obtain a nat from the constantly 42 function, you need to give it a nat. That's not true. Okay, so with this new ingredient, we can talk about refuting an arbitrary application on the left. I mean that it has a certain type. So if we want to refute that Mn has the type B, one way we can do this is as follows. We can first affirm, so here we're now on the right of the turnstile in this left-hand premise, affirm that M is a function that, well, if it was to give you a B like this, then you must have given it an A. And then all we need to do is refute that its actual argument is an A. Okay, so this is a kind of flavor of the type system rules that you get. But now let's return to my original application, which was somehow reasoning about incorrectness and giving guarantees about incorrectness in a type system. So for this, we introduce just a top type, the top of the subtype order, type of all values, because this allows us to state, if M has type OK, this is what we call it, then of course it means that M evaluates full stop. It reaches a value, because OK is the type of all values. So, and if we conclude that some term has type OK on the left, then we're refuting that the term reaches a value, that it evaluates at all. So here, we can refute that if you take the head of an empty list, that this will reach a value. And if it doesn't reach a value, this means, of course, that it either crashes or it diverges. So we're proving that this term either crashes or diverges. And how do we do it? Well, we use this application on the left rule because it's an application that occurs on the left-hand side of the turnstile. So we affirm that the head function, as we've seen, if you want to obtain a value from it, you must have given it a cons. But of course, it's easy to refute that the empty list is not a cons.
Yes,
so soundness in these kind of systems have two corollaries. So one is, of course, well-typed programs don't go wrong. Nothing has changed there. And because we have a top type, we can express well-typedness simply for some closed term M, simply as saying that M has this top type on the right-hand side of the turnstile. But then, of course, we have this symmetric case where you don't conclude that M is well-typed, that M has type OK on the right, but rather you refute that M has type OK.
No problem.
And we call M in this case ill-typed. And so we get this second tagline, ill-typed programs don't evaluate. In other words, an ill-typed program is guaranteed to either crash or diverge at runtime. Of course, we still have untypable programs. There's still plenty of programs we can't say anything about. This will depend on what your underlying type theory is like, how expressive your types are. Okay, so in the paper, as well as this kind of basic setup, I'd say we make three substantial contributions. One is developing the call-by value semantics and giving a kind of call-by value semantic analysis of this new function type in terms of like liveness and safety from verification. We look at the relationship with type complement and whether this could be seen as some kind of internalization of the two-sidedness, which it can't in a straightforward way. And then we also have a kind of case study because we want to sort of show that you could just take any type system and then give some left rules and you obtain this theorem. So we do this version with like a version of the Aiken-Wimmer's type system. And here we give like a syntactical two-sided version of progress and preservation. And we also show how to do automatic type inference, which is just kind of standard constraint generation and constraint resolution. Okay, thanks for listening.
So we have plenty of questions, and we're not going to have time for them all, but let's go ahead and get started. Try turning your microphone on.
Hello.
Hello.
Wow, that is super cool. So normally we have like a joint relationship between products and function types, and it gives currying and uncurrying. Is there something like that here for your necessity function type?
Yeah, I mean, I guess that there is, but I think, I mean, it's not something I've looked at, but I guess, you know, it would certainly make sense if you're in the situation. So one thing I mentioned is we have this second contribution is about internalizing negation. So but we have to use a different kind of semantics, which has disadvantages as well as advantages. But in that semantics, we can actually move everything that was on the left onto the right, and we just can obtain a one-sided system. So I think it would be easier to look at this question in that setting, because that'd be closer to kind of, it'd be more obvious the mapping to like categories and so on in that setting.
So we have an online question. I wonder if we could mark function types with a Boolean parameter that says whether the dependency on their argument is sufficient or necessary, and then read the usual rules in both directions.
So definitely you could do this. This would be one way, I guess, of representing it in a tool. I'm not sure about reading the rule in both directions, but I think I mean, this makes sense as a way of like maybe a more efficient way of doing type inference is just to track some Boolean on the type.
Very nice work. I'm here.
Hi, sir.
Have you considered adapting this to a dependently typed type theory?
Yeah, it's something I think something I'd definitely like to do, but not so far. But I don't see that there'd be any problem. Like, it's not obvious to me that there'd be any problem with that.
Hi. Hi. Thanks again for the wonderful talk. That was
no problem.
really interesting. One thing that I find comforting about a traditional lambda calculus judgment is that the sort of well-formedness of the judgment is baked into the judgment itself, where the variables that appear on the left are exactly the ones that are allowed to appear on the right. And through the talk, I was sort of not able to divine what the well-formedness properties of this two-sided judgment are allowed to be. So when do what variables are allowed to appear and where are they allowed to appear?
Mm-hmm. Yeah, so that's true. So so it can be a bit disconcerting, I think, at first. But I mean, you have to understand it really. So first of all, in our systems at least, they're just sets of formulas on the left and on the right. So there's no ordering there. And I mean, you have to just see it as a logical statement. So we're talking about models of this judgment. So, you know, a model will assign values to the variables. So the variables can occur wherever. You know, you can have variables that appear on the right but not on the left. That's also fine. But yeah, it is disconcerting. I agree. Yeah.
So we actually need to swap over talks. My apologies. I hear that we are really ready this time. We're getting lots of thumbs up. So let me grab a microphone.